Welcome to the deep dive. Today, we are plunging straight into the nervous system of modern artificial intelligence. Sequential decision-making.
That's right.
We're talking about the absolute cutting edge of reinforcement learning, or RL, the discipline of how we teach automated systems to, well, learn by trial and error.
And specifically, we're dissecting a fascinating duality that really defines the future of autonomy. First, how do we design the goal, the reward function, to capture human nuance and complexity? We need to move beyond just simple binary wins.
Right. Win or lose isn't enough anymore.
Not even close.
Yeah.
And then critically, how do we use the sheer representational power of generative AI, particularly these diffusion models, to actually express the sophisticated and diverse behaviors needed to achieve those deeply nuanced goals?
That's the perfect framing. The material we've synthesized for you today is, I have to say, incredibly dense. We're covering the foundational RL algorithms, the philosophical and practical debate around designing truly effective reward functions, the integration of generative AI.
And their concrete, real-world applications, especially in these high-stakes fields like autonomous driving and advanced robotics.
Exactly.
The mission for this deep dive is absolute clarity. We want you, our listener, to walk away with a clear, thorough, and highly informed understanding of what defines modern reinforcement learning today.
We're synthesizing these complex topics quickly but thoroughly so you are immediately up to speed on this, just an incredibly fast-moving field.
It really is.
Okay, so let's unpack this. We traditionally think of RL as being simply about maximizing cumulative reward. That sounds simple enough in a game of chess or
Fair, and a closed system.
But what happens when the goal is not just to win or hit a checkpoint, but to drive a car smoothly, maintain the right distance, avoid collisions, respect speed limits, and ensure passenger comfort all at the same time? That massive expansion in what's required is where the complexity truly explodes.
What's so fascinating here is the realization that the future of real-world decision-making hinges entirely on solving two critical interlinked problems. First, we need a reward structure that captures that necessary, almost human-level nuance, which we're calling the process. And second, we need a policy representation that is expressive enough to handle the inevitable uncertainty and generate diverse, high-quality, and multimodal behaviors.
And that's precisely why the diffusion approach has become so essential.
That's exactly it.
So let's start with the basics, because you really can't understand the challenges of modern RL without revisiting the framework. Reinforcement learning is formalized through something called the Markov decision process, or MDP.
Absolutely. The MDP is the mathematical language of RL. It's defined by 5 key components. You have the state space, which is all the possible situations the agent can be in.
Like every possible position on a chessboard.
Exactly. Then there's the action space, all the choices the agent can make. The state transition dynamics, which dictates where the agent goes after taking an action. The reward function, that's the feedback mechanism.
The carrot and the stick.
The carrot and the stick, precisely. And the discount factor. The entire goal of the agent is, on the surface, deceptively simple. To learn a policy, its strategy for picking actions, that maximizes the expected cumulative discounted reward.
And immediately, right there, within that formal structure, we confront the foundational difficulty of learning anything, which is the exploration versus exploitation dilemma.
This challenge is just inherent to any learning system in an unknown environment. The agent has to constantly balance 2 competing impulses. It needs to exploit known actions that have given it high rewards in the past.
Guarantee some kind of immediate return.
Right. But it also has to explore less known actions that might potentially yield even better, yet undiscovered results down the line.
So if it exploits too much, it gets stuck.
It gets stuck in a local optimum, a path that's good but not the best. But if it explores too much, it just wastes time and resources and never actually converges on a stable solution.
And this dilemma is magnified, or I guess mitigated entirely, by how we design that reward function. That brings us to the difference between sparse and dense rewards.
Right, and sparse rewards make the learning problem fundamentally harder because the positive signal is so rare. Imagine an agent in a really complex maze that only gets a +1 reward when it successfully completes the entire 100-step process.
And every other step is 0.
Every other step is 0. It's like searching for a single grain of sand in a desert. This requires just extensive, often highly inefficient exploration just to stumble upon that first positive signal.
Whereas dense rewards guide the agent more quickly, it gets immediate feedback, confirming it's on the right track pretty much every step of the way.
Precisely. A dense reward structure provides gradients towards success. The challenge, though, is that designing a truly comprehensive, continuous, and effective dense reward structure for a high-dimensional, real-world task like a self-driving car is almost impossibly difficult for a human to define without creating unintended side effects.
That difficulty is exactly why imitation learning, or IL, became so prominent, especially in robotics, right?
Absolutely. Imitation learning helps agents bypass that severe exploration problem. You just train the agent directly on expert human demonstrations. It's fast, it's effective. You are essentially giving the agent a dense prior knowledge on how to behave.
But I recall the critical drawback. When you use imitation learning, the agent struggles profoundly with generalization. It often leads to compounding errors. Why is that failure mode so catastrophic?
It's catastrophic because IL is inherently passive. It's designed to mimic the distribution of the expert data it was trained on. So if the agent encounters a state or a situation, maybe a slight skid on ice or a pedestrian appearing unexpectedly, that wasn't in those demonstrations.
It has no idea what to do.
It has no learned recovery mechanism. It doesn't know how to act outside that familiar data. And when it makes one small mistake, that error pushes it further away from the known safe trajectory, and then the next errors compound, often leading to total failure, a crash.
This inherent instability, combined with the difficulty of dense reward design, is what's driving this current philosophical shift in RL, the need to move from purpose-oriented rewards to process-oriented rewards.
Let's use automated driving to frame this. In a simple purpose-oriented reward scheme, you might only evaluate the terminal state. Success gets +1, failure, like a collision, gets -1. It's just binary feedback about the final objective.
But we know that simply arriving at the destination without an accident is totally insufficient for a commercial autonomous vehicle. It has to manage this hugely complex, simultaneous set of constraints.
That's the core insight. The system has to maintain the right distance, avoid pedestrians, obey speed limits, and critically, ensure a comfortable ride, meaning minimal abrupt acceleration or harsh braking. If a human passenger feels nauseous because the system is constantly slamming the brakes, the policy is a failure, even if it reached the destination. The process is the product.
And we saw this failure documented in early research with racing simulators. One common approach used a reward function that gave -1 for a collision, and then a positive reward based on velocity and alignment with the course.
Right, and that system had terrible stability. Well, the purpose-oriented part of the reward...
Maximizing speed.
Yeah. Exactly, maximizing speed. That was easy to learn. But collision avoidance was slow and erratic. The system didn't get enough corrective feedback during the process of driving near other cars. It only received this sudden terminal negative signal when it actually hit something.
Another racing example tried to incorporate the process by using a reward based just on velocity and the offset from the center of the course. It encourages speed and staying straight.
That's a bit better because it provides continuous, dense feedback, but it is incredibly inflexible. If a regulatory constraint changes, or if you realize that minimizing jerk, that's rapid changes in acceleration, is more important for passenger comfort than staying dead center, modifying that single amalgamated function becomes this massive engineering effort.
You can't just easily adjust the priority of one factor without retuning the entire equation.
Not at all. And this inflexibility is what motivates the general design scheme proposed by researchers like Goto et al., a highly adaptable, process-oriented reward structure.
Okay, so how does that work?
The scheme calculates an evaluation value for every single item we want to monitor, say, lane position, speed, and jerk. And it makes sure this value is bounded between 0 and 1. The final temporary reward is then determined based on the product of all those individual evaluation values.
The product approach. That feels like the crucial novelty here. Why a product and not a more intuitive sum?
It's all about non-compensatory performance. If you used a sum reward, an agent could perform extremely well in one area, for example, accelerating recklessly fast for a huge velocity reward, and that could mask a total failure in another area, like lightly bumping a wall for a small negative collision penalty.
So the net reward could still be positive.
It could. The system would learn that reckless driving is actually beneficial because high performance can compensate for safety violations.
But the product ensures safety constraints are absolute.
Precisely. If any single evaluation item fails, if the agent drives recklessly, hits an object, or violates a critical speed limit, the associated evaluation value for that item approaches 0. Since the final reward is a multiplication of all these values, that zero value instantly drags the entire cumulative reward down to near zero.
It forces simultaneous compliance with all constraints. It's a hard penalty for failure in any dimension.
It is, and that design provides incredible flexibility for future expansion.
Total flexibility.
You can easily plug in new evaluation functions for things like pedestrian proximity or traffic light status or vehicle stability. Because all the individual values are bounded between 0 and 1, adding a new metric doesn't cause a massive shift in the reward scale, which really stabilizes the overall learning process.
And if we need to adjust the priority, say we want to prioritize safety over ride comfort, how is that achieved within this mathematical framework?
That's handled beautifully by adjusting a tolerance parameter called alpha within the specific evaluation function template. To give a specific item, like maintaining safe distance higher priority, you just reduce the tolerance of that function.
And that does what exactly?
It makes the curve steeper. It means the evaluation value drops much more sharply, even for a small deviation from the optimal target distance. The agent is then strongly penalized for the slightest safety violation, and that overrides its motivation to seek comfort or speed.
I want to spend a moment on the actual structure of these evaluation functions because they are anything but simple. They use these complex exponential terms. Why the complexity? Why not just use a sharp cutoff or a step function?
That's a deep technical necessity for any modern gradient-based RL algorithm. If the reward function had a sharp cutoff, a step function, the reward would suddenly drop from 1 to 0. At that discontinuity, the gradient is undefined, or 0, or infinite.
Which would make gradient-based optimization unstable or just impossible.
Exactly. The exponential terms are necessary because they ensure the reward signal is continuous and smooth across the entire state space. And this smoothness provides a meaningful, continuous gradient that the agent can actually follow, even when it's approaching the limits of acceptable behavior.
So the complexity ensures stability. We are building in the physics of optimization alongside the physics of driving.
That's a great way to put it. They even design specific templates. For instance, evaluation functions might tolerate different offsets above or below a target value. For acceleration on a highway, you might have a different tolerance for harsh braking, which gets a very high penalty, than for gentle acceleration. They even have templates to manage items with 2 target values, requiring a sophisticated piecewise exponential function just to ensure mathematical continuity.
So the key takeaway from this first part is clear. For complex, real-world control, we must stop thinking about RL rewards as a simple single score. We have to view them as a continuous, mathematically complex function that is the product of many individual, finely tuned, process-based evaluations.
Now that we've established just how difficult it is to define success, let's review the foundational learning tools RL agents use to navigate these complex reward landscapes. We can focus on policy and value learning.
Okay, the major players are always PPO, which is kind of the gold standard for stability, and then the suite of actor-critic methods.
PPO, or proximal policy optimization, is absolutely foundational because of its stability and policy gradient methods. It is an on-policy algorithm, which means it only learns efficiently from data collected while following its current policy. Its major innovation is the use of clipping.
And the clipping prevents what?
It prevents massive, destabilizing policy updates. It calculates the ratio between the probability of an action under the new policy and the old policy. And by clipping that ratio within a defined range, say 0.8 to 1.2, PPO ensures that the new policy doesn't stray too far from the old one in a single update step.
So it makes learning much more robust.
Much more robust and efficient. That's why it's the workhorse for so many control problems, even though it's less sample efficient than off-policy methods.
And actor-critic methods, the combination approach.
Actor-critic methods are the synthesis of 2 functions. You have the actor, which is responsible for learning the policy, the rule for selecting actions, and then you have the critic, which learns the value function, how good it is to be in a certain state. By combining these, the critic provides a much lower variance estimate of the policy gradient, leading to faster and more efficient learning.
And we have soft actor-critic, or SAC, which is just everywhere in modern continuous robotics.
SAC is an incredibly robust off-policy algorithm. That means it maximizes sample efficiency by learning from stored experience buffers. It's designed specifically for continuous action spaces, and its central element is that it doesn't just maximize the expected return, it maximizes a trade-off between the expected return and entropy.
Right. Why introduce entropy? If the goal is optimal control, why would you explicitly encourage randomness?
That's the brilliance of SAC. Entropy is a measure of randomness in the policy. By explicitly incorporating it into the objective, SAC proactively ensures exploration. This prevents the policy from converging prematurely to a bad local optimum, and it keeps the learned policy broad and flexible. In complex robotics, that flexibility is crucial.
But doesn't maximizing randomness in a high-stakes scenario, like autonomous driving, risk erratic behavior, how is that volatility managed?
That's why stability mechanisms are integrated. SAC relies on two critical stabilizing tricks. First, the use of target networks, which smooth the learning targets. And second, the use of the mind double Q trick.
The mind double Q trick, we hear about that, but what is its function?
It addresses the problem of overestimation bias in Q learning. Traditional Q learning can become optimistic, overestimating the value of certain actions, which leads to instability. The mind double Q trick uses two separate Q functions, or critics, and when estimating the target value, it takes the minimum of the two estimates. This conservative approach drastically reduces that overestimation bias, making the value function estimates much more reliable and stabilizing the overall learning of the policy.
This foundational understanding of how value functions are updated brings us directly to temporal difference, or TD learning.
TD learning is perhaps the most fundamental advance in modern RL. It's a synthesis that achieves the best of both worlds. It combines the ability of Monte Carlo methods to learn directly from raw samples without needing a model of the environment.
With the power of dynamic programming, which updates estimates based on previous estimates, this is what we call bootstrapping.
Precisely. The agent is constantly using what it currently knows about the future, the estimated value of the next state, to update its estimate of the value of the current state. This bootstrapping approach is fast and provides continuous feedback.
What's the trade-off?
The trade-off is that it generally decreases the variance of the evaluations. It stabilizes the learning, but it increases the bias, because the estimates rely on the agent's possibly inaccurate existing estimates. For most practical applications, though, that reduction in variance dramatically improves overall learning performance.
Q learning and SARSA are the two major flavors of TD learning, distinguishable by their policy approach.
They showcase the classic on-policy versus off-policy distinction. Q learning is off-policy. It learns the value of the optimal action, regardless of the policy being used to collect the data. SARSA is on-policy. It learns the value of the action taken under the current behavior policy.
So let's pivot now from pure policy and value learning to planning, specifically integrating search methods like Monte Carlo tree search, or MCTS.
MCTS is often associated with games like Go, where it excels at long-horizon planning. At a theoretical level, MCTS, when it's sufficiently explored, becomes equivalent to Monte Carlo control. However, their evolution differs because the communities that developed them had different focuses.
MCTS researchers prioritize strong selection policies, like the UCB heuristic.
That's right. MCTS is optimized for selecting which paths to explore within the search tree, heavily relying on the upper confidence bounds, or UCB heuristic. The classic RL community, however, historically focused more on devising powerful mechanisms for updating knowledge, RTD methods, and worried less about the initial selection policy.
So what specific innovations does MCTS bring to RL theory?
Two critical innovations: playout and expansion. Playout involves executing a rapid simulation, often with a default policy, all the way to a terminal state to get a raw estimate of the reward. Expansion involves incrementally adding new, previously unmemorized state spaces to the tree structure. This is very different from classic RL, which traditionally only learned about states it had already visited.
This blend of learning and searching is formalized in the temporal difference tree search, or TDTS, framework.
TDTS is the powerful umbrella. It is a generalization of MCTS that incorporates the stability of TD learning, and it's an extension of traditional TD learning that brings in MCTS's ability to search. It's where search and learning truly merge.
And central to this merging is the eligibility trace decay rate, lambda, which we see in algorithms like SARSA UCP lambda. Can we clarify the difference between lambda and the discount factor, gamma? They both seem to diminish the impact of future events.
This is a point of frequent confusion, and it's critical to distinguish them. Let's use an analogy. Think of the agent as a person making life choices.
Yep.
The reward discount rate, gamma, defines the person's life philosophy. If gamma is low, close to 0, the person is impulsive, prioritizing immediate rewards. If gamma is high, close to 1, they are patient, valuing future rewards equally. Gamma changes the goal of the task.
And lambda?
Lambda defines the person's memory and learning style. It focuses purely on the backup mechanics. A lambda less than 1 enables bootstrapping and dictates how quickly a newly observed reward impacts previous state estimates. It changes how the knowledge is updated. For many tasks, we often set gamma to 1 because we want to maximize the final win, but we still tune lambda to improve the stability and speed of learning.
That distinction is incredibly helpful. So we have these robust canonical algorithms for learning and search, but both still hit a wall when the optimal behavior itself requires complex, diverse, and multimodal responses, a scenario that demands a more expressive policy representation.
Which leads us directly to generative AI.
This shift represents the modern frontier of RL. We are replacing these rigid traditional policies that might output a single best guess, with policies that can represent highly complex multimodal probability distributions. And diffusion models, or DMs, are the generative engine making this possible. DMs are best known for creating stunning images, like with Midjourney or Stable Diffusion. How do we take that image generation capability and recast it as a sophisticated decision-making tool?
It all boils down to their core mechanism of structured noise and structured denoising. DMs operate via two sequential processes. The forward process is simple and fixed. It systematically perturbs a data point, which might be an image or, in our case, an entire sequence of actions or a trajectory, by gradually adding controlled Gaussian noise over a sequence of steps.
Okay, so it's just controlled destruction of the data.
It is. If you run this process long enough, the original data is completely destroyed and becomes just standard, pure Gaussian noise. The reverse process is the magic, the generative part. This is where the neural network is trained. It learns to reverse that noise application step by step.
So it learns to predict and subtract the noise at each step.
Precisely. It iteratively reconstructs the original clean data from that totally noisy sample.
But why are DMs so necessary for RL? Given the sophistication of SAC and PPO, what foundational problem of decision-making do DMs solve that classical methods just cannot?
They solve the problem of expressiveness. Conventional policies, especially those used in continuous control like Gaussian policies, are inherently rigid. They are unimodal, meaning they only model one primary best action or behavior. This is fundamentally inadequate for complex real-world tasks.
Because in the real world, robotics, driving, manipulation, there are often multiple equally good ways to solve a problem.
Precisely. That's multimodal behavior. For a robot tasked with grasping an oddly shaped object, there might be 2 or 3 equally feasible grasping solutions. For an autonomous vehicle navigating a construction zone, there might be several safe trajectories. A traditional unimodal policy can only find one of these, and if it finds a suboptimal one, it gets stuck.
And DMs handle this naturally.
Yes. DMs naturally represent these complex, multimodal action or trajectory distributions because the noise input can be denoised into any of the valid modes. The agent can then sample from this diverse set of possibilities, which vastly improves exploration and the versatility of the final learned policy.
Beyond expressiveness, you mentioned DMs also offer significant benefits during the training process itself, particularly regarding stability.
Yes, the training objective in DMs, which is essentially a sequence of denoising tasks, creates much smoother optimization landscapes compared to the notoriously spiky, high-variance loss functions of many traditional RL algorithms. This enhanced stability is critical for generalization, especially in offline RL, where the agent learns purely from a fixed, pre-collected dataset.
And finally, they enable a fundamentally higher level of reasoning trajectory level planning.
Instead of a policy just selecting the next action based on the current state, a diffusion-based policy can be trained to generate full sequences of actions and states over a long horizon, conditioned on a high-level goal. This shifts RL from just reactive action selection to proactive long-term planning.
Let's break down the functional taxonomy. How are these diffusion models actually integrated into an RL system?
We categorize their integration into 3 primary functions. The first is trajectory optimization, often seen in frameworks named Planning Diffuser or Just Diffuser. Here, the entire RL problem is reformulated as conditional sequence generation.
So the DM is generating the plan, not the immediate action.
Correct. The DM is trained on a dataset of high-reward or expert trajectories, and it learns to reconstruct a clean, successful sequence from one that has been corrupted by noise. During inference, you condition the generation on the desired outcome, a goal state or a target reward. The DM then effectively plans the path to achieve that outcome.
The second category is policy learning applied at the action level.
In this case, the DM is only generating the next action, conditioned on the current state, much like a traditional policy. The action itself is the object of the denoising process. This is the approach used in systems like diffusion QL, where the rigid Gaussian policy of SEC is replaced by a diffusion policy, allowing the system to sample from complex, multimodal action distributions at every single time step.
And the third approach is function guidance.
This is fascinating because it leverages the diffusion process itself for control. You incorporate external knowledge, like a learned Q function or a reward signal, directly into the reverse, the denoising process. The Q function's gradient guides the DM to bias the generated actions toward those that predict high returns.
So even if the DM suggests a plausible path, the Q function acts like a filter, ensuring the final sampled action is a high-value one.
Precisely. It provides a real-time, principled mechanism for incorporating learned value information directly into the generative policy, combining the expressiveness of the DM with the optimization power of RL value learning.
Moving from theory to deployment, we encounter the immediate critical bottleneck of implementation, latency. Diffusion models, due to their iterative nature, are inherently slow, which is, lethal in real-time control systems like robotics.
It is the single biggest challenge. The time required for the iterative sampling process of DMs seriously hinders real-time robotics. To mitigate this, researchers are focused on optimizing the denoising network architecture, which is generally one of three types, each with pretty severe trade-offs.
Let's start with the dominant choice. Temporal U-nets.
Temporal U-nets are the standard choice because they are derived from the stable U-net architecture, which was so successful in image generation. They replace standard spatial convolutions with one-dimensional temporal convolutions, making them suitable for sequence data like trajectories.
And they're stable?
Very stable and less sensitive to hyperparameter changes. But their internal structure leads to a performance issue in high-precision tasks.
Which is the over-smoothing effect.
That's it. The convolutional structure tends to aggregate and average information across the time axis, which can inadvertently smooth out high-frequency dynamics. When a robot requires precise, rapid velocity control or sharp, decisive movements, this smoothing effect diminishes performance.
Which is where the power of transformers comes in, ideally suited for sequence data.
Transformers, leveraging the attention mechanism, are proficient at capturing long-range dependencies across a sequence. This makes them incredibly robust at handling high-dimensional data over long horizons, which is critical for high-level decision-making.
But their cost is immense.
They demand a substantial computational resources for both training and inference, and critically, they suffer from prolonged inference times. For a robot operating at a real-time control rate, say 100 Hz, the latency of a transformer-based DM can be a non-starter.
And finally, MLPs, the simplest architecture.
MLPs are superior in terms of sheer computational efficiency. They're much faster for sampling. However, their performance drops off dramatically when dealing with complex, high-dimensional inputs, especially raw images, which are common in visual robotics.
So the community has to choose between fast, slightly imprecise U-nets, powerful but slow transformers, or lightning-fast but input-limited MLPs.
Exactly. The solution to mitigating this latency is often found in the sampling method itself, using faster methods like DDIM, which reduce the number of required denoising steps.
Let's discuss a core application: trajectory generation and robotic manipulation. DMs are excelling because they inherently understand that there isn't just one right path.
The ability to model multimodal distributions is their killer feature here. In complex manipulation tasks, there are often redundant solutions, multiple equally valid trajectories, or grasping solutions that succeed. By capturing all these modes, DMs increase the robot's flexibility and dramatically improve its generalization capabilities.
When planning, the DM has to decide how much of the future to predict. What are the trade-offs between predicting the whole trajectory versus just individual steps?
Predicting the whole trajectory at once is computationally efficient. You run the DM once, you get the entire plan. However, it prohibits adaptation. If the environment changes suddenly, a new obstacle appears, you have to discard the entire plan and rerun the time-consuming diffusion process.
That's unacceptable for dynamic real-time environments.
Which is why receding horizon control is often preferred. The agent continuously generates a short sequence of micro-actions, adapts to the new observation, executes the first action, and then regenerates the plan. This allows for excellent adaptation, but has the drawback of increasing compounding errors.
Some researchers take a really radical approach, framing trajectory planning as image generation.
It's highly innovative. Instead of training the DM to map visual input to a low-dimensional action vector, they train it to predict a sequence of images that depict the change in the robot's and object's positions over time.
Wait, so the robot is planning a movie of its future success?
Essentially, yes. And the profound benefit of this image space planning is that it unlocks massive generalization. You can leverage internet-wide video training data, which provides immense diversity. Crucially, it sidesteps the notoriously difficult problem of mapping high-dimensional visual observations to lower-dimensional action space vectors.
The trade-off must be immense resource consumption.
Absolutely. You need extensive training to ensure temporal consistency and physical plausibility in the generated movie.
Focusing specifically on grasp generation, DMs are now modeling complex 6-DOVIF poses. What makes the SE3 group essential here?
6 degrees of freedom refers to the 3 translational coordinates x, y, z, and the 3 rotational coordinates needed to fully define the position and orientation of a rigid body, like a gripper. The SE3 group is the mathematical structure that simultaneously describes both rotation and translation in 3D space.
Why not just use standard Euclidean coordinates for position and Euler angles for rotation?
When you try to interpolate or diffuse in a standard Euclidean space, you can easily generate non-physical, nonsensical poses, especially with rotation. Working within the SE3 Lie group guarantees that the diffusion process respects the geometry of rigid body movement, enabling continuous, smooth interpolation between multiple poses, which is absolutely crucial for generating physically grounded actions.
Finally, let's look at coordination. DMs are being integrated into multi-agent reinforcement learning, or MRL.
MRL environments are fundamentally unstable because they're non-stationary. Every other agent is also learning and changing its policy. DMs help stabilize policy updates and improve coordination. We see 2 primary approaches for this.
The first, joint trajectory generation, sounds like centralized control.
It is. A single DM models the joint trajectory distribution across all agents simultaneously. The policy is learned by observing the coordinated successful behavior of the entire team. This is excellent for ensuring highly synchronized cooperative behaviors like autonomous platoons driving closely together.
And the second, collaborative policy learning, is decentralized.
Here, each agent independently learns a diffusion-based policy based only on its local observation. The DM allows individual agents to reason over complex multimodal action spaces based on limited information. This improves adaptability in competitive or partially observable environments like drones, swarm control, or edge computing.
The final frontier is the deployment pipeline. Everything we've discussed hits a wall in the real world due to the notorious sim-to-real gap.
This is the problem where a policy trained in an ideal, noise-free, and precisely modeled simulation fails spectacularly on real hardware due to unmodeled physics, subtle differences in friction, sensor noise, latency delays.
Or just lighting conditions. The simulator has to be similar enough.
Addressing this is paramount. We're seeing innovative approaches like the Rialto pipeline, which proposes a real-to-sim-to-real cycle leveraging digital twins.
I find the concept of creating an on-the-fly digital twin fascinating. How does this close the gap more effectively than traditional high-fidelity simulators?
Traditional simulators, while detailed, still rely on human engineers manually tuning thousands of physical parameters. The Rialto approach uses easy-to-deploy tools, like standard phone cameras, to capture the real environment and rapidly construct a digital twin that matches the real world dynamically.
So the robot is now training in a simulation that is visually and physically almost identical to its current physical surroundings.
Exactly. This allows the robot to train robustly in simulation, where data collection is fast and safe. Researchers found they could collect the equivalent of 100 days' worth of real robot interaction data in just 3 hours of GPU time. This approach minimizes the dependence on expensive, slow, and potentially hazardous real-world interaction.
And DMs themselves contribute to bridging this gap through sophisticated data augmentation.
Since DMs are generative, we can use them to augment real-world training data. We can sample new images where textures, colors, or distractors are changed. The crucial difference here is that DM-generated augmentations are constrained by the learned real-world data distribution.
Unlike traditional augmentation methods that might generate implausible or ungrounded data.
Yes, traditional domain randomization requires complex manual tuning. DM augmentation ensures the data, while varied, remains grounded in the physical world, creating more robust policies without needing that fragile tuning process.
Now let's get into safety. In high-stakes applications, DMs must adhere to constraints, safety thresholds, Energy budgets, obstacle limits. They can't just sample the fastest action, they must sample the safest one. How do DMs handle this?
They integrate constraints directly into the generative policy using guidance mechanisms. The first method is classifier guidance.
Okay, let's use an analogy to clarify this. If the DM is the planning system, what is classifier guidance?
If the DM is the policy trying to generate a sequence, classifier guidance is like having a separate, expertly trained referee watching the process. You train a separate model, the classifier, whose job is solely to score the generated trajectory at each denoising step on how well it satisfies a specific constraint, like staying 10 feet from an obstacle.
And the output of that referee model then influences the planner.
Yes. The system uses the gradient of that safety score to steer the generated actions toward the constraint-satisfying regions. If the trajectory starts heading toward a wall, the classifier penalizes it, and that penalty gradient nudges the DM back onto a safe path.
That sounds effective, but computationally heavy.
It is. It requires the training of an additional separate model, which adds significant computational cost. Furthermore, the guidance factor, weight, how much influence the referee has, must be painstakingly tuned.
That leads to the alternative, classifier-free guidance. How is that different from our trained referee?
Classifier-free guidance is like training the player with and without the referee simultaneously, and then blending the behavior on the field. Instead of training a separate classifier, you train two diffusion models in parallel for each constraint. One conditional DM, trained to hit the goal and satisfy the constraint, and one unconditional DM, trained only to hit the goal.
And during sampling, you blend the two outputs.
Exactly. During sampling, a weighted mixture of the outputs from both DMs is used to enforce the constraint. You can amplify the difference between the constrained and unconstrained predictions to strongly steer the action.
The primary benefit being the ability to combine constraints arbitrarily.
Correct. You can define multiple constraints, speed, safety, comfort, and mix them flexibly during inference, even those that weren't seen together during training, which provides immense operational flexibility. The major caveat, however, is that you still can't generalize to an entirely new constraint unless you retrain.
Even with all these advancements, the sources highlight major remaining challenges that are keeping this technology from widespread deployment.
The biggest hurdle is absolutely generalizability. DMs often struggle to generalize to entirely new tasks or unseen states that deviate significantly from their training distribution. The policies are powerful, but can be highly tailored, almost brittle.
And the classical RL challenge of long horizon planning and sparse rewards hasn't vanished either, even with trajectory generation.
Not at all. DMs still struggle with credit assignment over very long time horizons. If the reward is sparse and received far in the future, it's hard for the iterative denoising process to trace back precisely which actions were responsible. A promising future direction here is hierarchical modeling.
Where the DM handles the low-level mechanics.
Yes. In hierarchical RL, large language models can be integrated for high-level reasoning setting sequential goals or abstract plans, while the low-level diffusion modules handle the execution detail, generating the fine-grained actions to achieve those sub-goals. It breaks the long-horizon problem into manageable chunks.
And finally, there's the issue of theory-chasing practice. Despite the incredible empirical success, the theoretical foundations are struggling to keep up.
That's critical for reliability. Unlike classical algorithms where convergence properties can be formally established, DMs involve iterative denoising coupled with high-dimensional stochastic dynamics. We currently lack formal mathematical guarantees regarding convergence, stability, and variance. We know they work remarkably well, but we don't fully understand why they converge so reliably.
We must also address the non-technical challenges raised by the sources, specifically around the alignment of these powerful systems with human intent.
The sources raise the primary concern of unintended consequences from reward misalignment. RL systems are optimization machines. They strictly pursue the reward signal they are given. If that signal is poorly defined or fails to capture the full scope of human values, which we've spent this entire dive discussing how hard that is, the system may adopt harmful behaviors to achieve its goal.
The classic example is an agent maximizing a proxy metric for success, which instead leads to negative outcomes.
Exactly. If a system is tasked with maximizing a proxy for user engagement, it might find that promoting divisive content maximizes clicks, achieving its technical goal but violating broader societal values. Since the decision-making process of DMs and complex RL algorithms is inherently opaque, this directly impacts transparency and accountability.
Right.
If a system relying on a diffusion-based policy causes unexpected harm, especially in autonomous driving or healthcare, determining where accountability lies becomes extremely challenging.
The consensus seems to be that robust and transparent evaluation and accountability frameworks must be established alongside deployment.
That's the consensus. We must ensure that the evaluation protocols and mechanisms for auditing the decision process catch up to the sheer computational power and capability these systems now possess.
What a dense and illuminating journey. We established that the mathematical core of modern RL is shifting. We have to move beyond simple, purpose-oriented rewards to highly complex, product-based, process-oriented reward functions tailored for tasks like automated driving.
Ensuring that performance across all constraints is non-compensatory. And we learned that the policy itself is undergoing a revolution. Diffusion models are moving RL past rigid, unimodal policies, offering the multimodal expressiveness and trajectory-level planning capabilities necessary for robotics and multi-agent systems.
These are just immensely powerful tools, provided we can manage the practical challenges of speed, constrained adherence through sophisticated guidance, and closing that persistent sim-to-real gap.
This deep dive revealed that critical duality, the necessary shift in defining what success looks like, which is the reward function, and the deployment of generative AI to define how to achieve it, which is the expressive diffusion policy.
And if the fusion of complex, multi-item reward functions and opaque, black box generative policies is rapidly becoming the standard blueprint for autonomy, that leaves us with this final, provocative thought.
We are witnessing the empirical success of these systems far outpace our theoretical understanding and our ability to formally verify their safety and stability. For universal deployment, how do we ensure that the rigorous mathematical foundation of these new learning systems is secured before we delegate critical, high-stakes decisions entirely to them? That balance between capability and certainty is the next great frontier.